Welcome. In this video I'm going to show you how you can determine Hedges G for a one sample t-test, which is an effect size measure that could be used instead of Cohen's d. It's actually an adjustment of Cohen's d. I'm using Python 3 using JupyterLab via Anaconda, and the exact version I'm currently running is Python version 3.912, but it should work with most other 3 versions as well. The Hedges G is, as mentioned earlier, an adjustment for the Cohen's d, and this could be used, usually it's often seen for a pair test, but it can also be done for a one sample test. We can also then use the interpretation similar as to the one sample Cohen's d, for which again we then need to adjust it by multiplying with the square root of 2. Alright, so how can you calculate this with Python? Well, to show you I'll need an example. For that I'll need pandas to read the file. If you've never used pandas before, you can use pip install pandas and then you can import it. The data I'm going to be using is from the General Social Survey from 2012, which I slightly adjusted just for the examples here. Alright, so this is what all that data, or the first 5 rows, look like. It has 706 columns, so we're also not seeing all of them. I actually only need one column for this example, which is the age, because I do need a numeric field. I'm going to be removing any missing values. I'm going to replace one category that was labeled 89 or older with 90. Not sure why I did that. Could have used 89 or something else. But with replace, that's easily done. And then because all the numbers appear actually as strings, I'm going to be using toNumeric to make it all numbers. So that's what's being done in this little code block so that I have a nice clean numeric field. I need a hypothesized mean, so I'm just going to set that to 50. Alright, then the sample size is also going to be useful. I can use the len function, which I probably think is short for length, and apparently there are almost there are 1969 cases. The degrees of freedom is simply the sample size minus 1 for this, so I can define it as n minus 1. The mean, the average is needed, so it's simply to add everything up and then divide by the sample size. Pandas actually has a mean function, but if you don't want to use that, you can use the sum and then divide over the earlier found sample size. So as you can see, they both produce the same result. The standard deviation, the sample standard deviation, is the sum of the square differences between each score and the average, and then square each result, sum all of that up and divide by the number of items minus 1, so the degrees of freedom. Again, pandas has us covered, so there's a standard deviation function. Always check this does indeed divide by n minus 1 if you don't tell it otherwise. So I can actually use that function, and just to show you that it gives the same result, again here I've used the formula. To the power of a half is the same as taking the square root of something. So these two again give the exact same result, except for the end where there's probably some rounding errors going on. Now, as mentioned earlier, Hedges G is a correction on Cohen's d, so we do need Cohen's d, which for one sample case is the average minus the hypothesized median divided by the sample standard deviation. So in this case it's about minus 0.1. Hedges G says, well, it's going to be approximately that Cohen's d multiplied by 1 minus 3 over 4 times the degrees of freedom and then minus 1. So that's fairly straightforward. You can just use that in Python, calculate that exactly the way that formula is shown here. The exact is a little bit more complicated. It uses a so-called gamma function of m, where m is then the degrees of freedom divided by 2. Often you'll actually see m being the degrees of freedom, so you'll see in the formula then stating m divided by 2. I'm using df for degrees of freedom and simplify the formula a little bit here. The gamma function is a bit trickier. If you have a value, if it's an even number, then it's actually that even number minus 1 simply factorial, and otherwise you have to do this scary one, which is 2 times then the number factorial divided by 4 to the power of a times a factorial times the square root of pi. Now m is easily calculated, that's just the degrees of freedom over 2. And for this gamma function, Python actually has a math library that has the gamma function, so we can just import math. We don't need to install it. It should come with Python, and then we can just run this function. Unfortunately, though, it quickly becomes out of bounds. So this is giving us an error because m is too large. So in this case, it would have been 984 for m. That's over here, and that's way too large for Python to calculate. The threshold is, I think, at 171, so 171 still works. 172 gives an error. So you could use this. Perhaps there are other ways around it and do the real math on everything to find the exact value, but usually the approximation is good enough. If you reach n is bigger than 50 or so, then even it gets close to 1. Now, very often you will see actually the formula mentioning like this, but that's more for paired samples, where n is then actually, where the degrees of freedom is actually then n minus 2. And if you do the math, 4 times the degrees of freedom minus 1, if the degrees of freedom would have been n minus 2, you get 4 times n minus 4, 4 times n minus 4 times 2 minus 1. That's of course the same as 4 times n minus 8 minus 1, and that's then the same as 4 times n minus 9. So that's the same formula, just slightly different because of the degrees of freedom being defined slightly different. Durlock also has one for Cohen's d. He uses this formula as an adjustment. I checked; it's not the best. I think it's not as good as Hedges' own original version, but okay, it's another version you might come across. And a far scarier looking approximation would be from Xu. Not sure if I pronounced that correct. This should be approximately, of course, d times the 12th root out of all of this. And yeah, that one works really a lot better. So I made a small function for myself on this, which only needs the math library. It goes over all the steps exactly as before. And has all the different options. It does check if m is not too large, and if it is too large, it uses the Xu approximation, which is the one if nothing else is specified. The default method here is actually exact. I set it up as method to be exact used. For the interpretation, it needs to convert the value to the regular Cohen's d, as it were. So you multiply it with the square root of 2, which is the same as raising it to the power of a half. And we look at the absolute value. Cohen's d then actually gives an interpretation table. Below 0.20 can be considered negligible, below 0.5 small, below 0.80 medium, and everything else is large, and it returns those two. All right, and let's see if it works. It gives me a warning because I want it exact, the default, and the sample size is simply too large, so it's using 2 approximation, and this is the same result as we saw earlier, and it's apparently a really small effect size. It has a little bit of a helper function even in there, or a help information, and these were the references used. All right, so that's it. I hope this was helpful, and thank you for watching.